Okay, thank you, Nicolò, for your kind introduction. Well, my name is Sergio Herraiz. I'm going to present the results of the tools that the University of Girona developed during the Dayland project. So just for introduction, the project, Dayland project, this is the acronym for the Integrated Multi-Vector Management Systems for Energy Islands, was a European project from 2019 to the end of the 2022. Development in the project was the aim of the project was development of several tools, technological tools, societal tools, and business tools in order to support the decarbonization of energy islands and isolated communities. The construction was made by several, well, as you see the partners here, companies from Greece, Switzerland, Norway, Spain. I'm going to talk about the first block, the development of the technology tools to support this decarbonization of energy islands. Just, well, I will show you an example. Just take into account this. One of the objectives of the project was to work with couple sector couple vector sectors, energy sectors like electricity, hydrogen, and with the aim to develop optimization tools to optimally manage different types of storage systems. This is the approach of these ELAN tools for the three levels: the community level in red, the business level in green, and the technology level in blue. The idea is that all the information, all the data was collected from the devices in the field through a middleware, in our case an enterprise service bus. And the tools we are going to present and talk about is that related with the short-term operation tools. In the project, there were tools for planning, to calculate, or to give let's say, advice how to make the investments in distributed energy resources in the systems. And our part in the University of Girona, the tools that were developed by my research group, the Control Engineering and Intelligence Systems group, was consisted of three different models. The approach in the project that these tools are modular and then can combine to, in this case, to optimize the use of the distributed energy resources in the local area systems. I will talk about the optimized scheduler, the energy forecaster, and the data preprocessing application tool. So these tools, this slide, just want to present the objective of those tools. The ELAN toolbox, the technology part, the aim is to calculate when and how to consume and store energy to optimize the use of the locally distributed energy resources that exist in the local energy systems. Taking leverage from the module that is devoted to forecast both the demand and the generation. Also, using the data from the field, and this means that the data maybe needs and some kind of preprocessing to improve this quality, and integrate these three modules by means of this enterprise service bus in order to communicate with the field devices. And considering these scenarios that consider not only electricity, but electricity, hydrogen, thermal, electromobility. The tool is based, of course, that in the local energy system exists a set of dispatchable assets that can be controlled in order to optimize asset objectives. These objectives can be peak shaving, maximize self-consumption, maximize the percentage of renewable energy that is generated inside the energy system. Scheduling these dispatchable assets, taking into account the operational constraints that can exist. And in a scenario that comprises basically the day ahead, or it can be adapted to intraday scheduling. The first tool, the optimal scheduler itself, then provides the plans for the controllable assets in the local energy systems, the EV chargers or the electric energy storage systems, based on the energy that is forecasted to be produced and to be consumed. So in the left in the slide, the inputs are shown, the demand forecasting for those consumptions that are not dispatchable, that are not controllable, the forecasting for the generation inside the energy systems, the constraints of the different assets, the status of the dispatchable assets, the forecasting of the weather, and also can be included the energy prices, the day-ahead energy prices for the electricity. The tool, the algorithms are based basically in, let's say in this case, in the solution was based in genetic algorithms. So the optimal scheduler core performs simulations of the candidate solutions in order to minimize this fitness or this cost function, to minimize an objective to be achieved by the optimal scheduler. For making a little more clear the presentation, I will present the case for one of the three pilots in the project. The pilot in the lab project, there were three pilots. One pilot in Spain that is going to present is a technology park. Another pilot was in Romania, university campus, and the third pilot was a harbor, a Norwegian harbor. So I'm going to present just to be more precise the case that we develop and implement for the Spanish pilot site is the Wildcat Technology Park. In this case, the local energy system, the technology park counts with an electrolyzer that can generate hydrogen. It also counts with a hydrogen refueling station for fuel cell vehicles. It counts with electrical charging, charges for electric vehicles, and in this case, a part of the thermal system, in particular the cooling system, was also included. In the park also there was or is photovoltaic generation and wind generation. This will be the structure of the optimal scheduler, the inputs, the outputs, the variable status control, and the cost function. This is a general overview of the structure on the architecture in the optimal scheduler, and this will be the case of the particularization from the Spanish pilot site. So we have to forecast the production, both the wind and photovoltaic production, to forecast the consumption in different buildings in order to control, in this case, 4 assets: the electrical vehicle chargers, the hydrogen station together with the refueling station, electrolyzer, and the chiller, one part of the HVAC system. As inputs, also those information from the pilot as the status of the hydrogen tank, information from the thermal system, indoor and outdoor temperatures, consumptions, and also in this case the price of the electricity. And finally, on the right in the slide, the constraints for each of the 4 controllable assets. In the case, for example, for the electric vehicle charging, that's the time range that the users can charge their cars, the maximum cars that can be charged simultaneously, the number of chargers, the minimum required energy for each car. So on this right side of the slide shows from each asset which are the constraints, if there is minimum time of operation or capacity of the hydrogen tank, or for the chiller the set point temperature, etc. Based on real data collected in the system, we simulate the results they present simulated, but it's based on real data in order to generate the scheduler for 2 weeks. This is an example of the inputs required for the forecasting module. I will talk later about this module, about the information provided by the external data provider, in this case the electricity prices, the weather data, the forecasted, in this case, temperature. Also provided by the external service, some static information about, in this case, the selling prices for both for electricity and hydrogen, and the status of the hydrogen tank. As a result of the optimized scheduler, we got the 3 scheduling plans, in this case for the day ahead, and a resolution from 1 hour, when to produce hydrogen, how much hydrogen to produce, if the system, the chiller, in this case, in the HVAC system is working or not, when to charge the electrical vehicles, and when to generate hydrogen, or when more than generate hydrogen, when can be used this.
Pues le digo a Sabrina que no pasa nada.
The simulations, in this case, this slide shows the simulated behavior of these controllable assets together with the generation assets in the local system. This minimization of the cost function, in this case, the target was to reduce the cost of the electricity that should be needed in the system. So this was the criteria in this example, to reduce not only the amount of electricity from the grid, but also to reduce the bill that is going to be paid from this electricity. Since for the optimal scheduler is needed, this forecasting is needed to the energy, both the consumption and the generation, to be forecasted. And a second module was developed that is objective is to create the models for forecast in this day ahead horizon with a 24-hour resolution, the demand and production in the energy system. In this slide, you can see the 2 levels. Let's say that this model works, the first levels to create the models based in historical data, both energy data and weather data, and also some contextual data, for example, the working days, working hours, etc., just to create the models for the controllable assets, not controllable assets, demand, and from the generation. And the second level to forecast these values, making use of these models, and together with the models are data-driven models. So in this exploitation phase, to create this, to obtain the results, also are needed historical data, let's say energy data close to the day that is going to be forecasted. Of course, the weather forecasting data and also this contextual data based mostly in calendar and timetables. This is in this slide, I would like to show the approach for the consumption forecasting based on time series data-driven models based in this historical data that is gathered in the field, making use of different algorithms. In our case, we try to choose the best algorithm that fits with the data that we are working on. So the algorithms can be neural networks or super vectoral machines, etc. In order to train this model, in this case, those just an example of the, let's say the sorry, the real consumption and the consumption forecasted. In this case, just of course to choose the best model or to retrain if it is needed the models over the time. So the indicators as mean absolute percentage error or correlation, coefficient correlation are used. For the generation, the models are based also in data, but combines physical expressions. Let's say, for example, not to consider all the specifications for the the fabricant of the PV panels, for example, just maybe physical expressions that relates the radiance with the production, the efficiency in order to using historical data adjust some parameters in the model. In this case, thus we have this the let's say the figure from the real PV from one day and the forecasting, and in this case the blue line corresponds to the global irradiance. The third module I would like to talk is this data preprocessing application that takes into account that the data that is gathered in the field may contain errors, or maybe some lack of data, maybe contain some errors, maybe also may need resampling from the frequency that the data is gathered with the frequency that is used by other applications. In this case, just to resample to get a granularity of 1 hour. And this tool does perform all these functionalities. In the right side of the slide, there are the four functionalities that has been implemented in this module: the detection of outliers, the imputation values. If there is not a value, of the value is considered an outlier, imputation a new one that improves the quality of all data sets, resampling and profiling. In this case, this slide, you can see two examples. The left side, the outlier detection and the value imputation, and in the right side, the energy profiling, just to more, let's say, longer historical of data to get a profile that can be used afterwards in the forecasting models. So just summarizing, the tools that we develop in the ILAM project, the main one is the optimized scheduler. The other ones are tools that are needed for the optimized scheduler. As the solution is modular, you can use, if you only want the forecasting, you can use this module separately from the OS, or you can use the data preprocessing module just to improve the quality of the data. This is the development model tools approach. The software developed software as a service with this multi-vector local energy systems approach. In this case, electricity, hydrogen, thermal system. And if you are more interested in reading this case, so you can get this publication in the Journal of Cleaner Production that explains more in detail the tools, talking about the algorithms or the methods that were used to implement each one of the modules, and other information related about the goodness of, for example, the forecasted values. Nowadays, the research group continues working in this topic, developing this kind of tools, focusing in energy systems. We are just started. This the first year of the project. Another European project is called Reschool, is oriented to energy communities, but the idea is also, of course, developing these tools that can help to make these energy communities more efficient and active in using the energy that are producing, and making use of these assets that can be dispatchable assets, not only consumptions, but only the storage assets. So with this concludes my presentation. Thank you for attention. I don't know if now at the end of the webinar, if there's any question or something to want to know deeper.
Thank you, Sergio, for the detailed presentation on the ELAN tools that were developed during the project. So I propose we gather all the questions at the end of the webinar so that we just have all the questions all together. And now I can give the floor to Paul. So please, Paul, feel free to share your screen.
Yes. Hello, everybody. Can you see my screen or not yet?
Yes.
Yes.
It's fine?
Yes, we do. Yes.
Okay, perfect. Thank you. So good afternoon, everybody. So I'm here to talk about the Insular investment planning tool that I will present right after. As an introduction, yeah, just the agenda for the presentation. So we'll just first have a really short introduction about the Insular project, where the IPT tool have been developed. And after I will continue with the presentation of the tool, introduction, a bit of some elements regarding the energy system modeling that is done within the tool, and after a short demonstration. And finally, just one slide about commercialization roadmap of the IPT if you are interested to have more information, and well, if you are interested in the tool also. So first, maybe one word regarding Artelys, because maybe you don't know the company. So we are an independent company founded in, well, a bit more than 20 years ago, specialized in decision support, modeling and optimization. We are especially working a lot in the energy modeling field. We are working, for example, for the METIS project for the European Commission, modeling EU energy system, working a lot on different kind of software dedicated to energy system modeling. And that's why we have been involved in several research projects for, well, for the EU, and especially the one I will talk about today, the Insular project. So a few words about the project. So it was an Horizon 2020 project, started a bit more than 4 years ago, and basically we just finished the project at the end of last month. We had our final event at Artelys that gathered like 26 partners, 10 countries, and a bit more than 12 million total budget. And we are different, so it was dedicated on the decarbonization of different islands in Europe. So we had 3 lighthouse islands within the scope of the project: Madeira, Unier, and Bornholm. And after 4 follower islands, Norderney, Menorca, Sala, and Maligaland, where we had the opportunity to test the IPT and to replicate the different use cases of the project. So we'll not talk a lot about the different use cases, but we have a very important range of different use cases investigated in the scope of the project. In a very small island, Unier, a large one, Bornholm, and a quite large one, Madeira, with different specificities. So I will not really go into the detail of these use cases because it's not the point of today's presentation. And I will focus on the investment planning tool that have been designed in order to replicate these different use cases in other islands. And well, the one of the project which has been the follower islands, but also after the point is to be able to replicate this in other islands. So when I'm talking about the investment planning tool, what I'm talking about, so it's a web-based software that we have developed within the Insular project in order to assist island decision makers to design their energy strategies and to monitor the impacts on insular energy systems. So at the opposite of the previous tools that have been presented, here we are really focusing on long-term investment planning. So it's not short-term, it's really to assess, for example, how to reach carbon neutrality in 2050. So it's kind of like very, very long-term. So it's divided in 2 modules. So the first one called the Island Modeling Assistant. It's used to represent the current state of the island energy system you want to, well, to analyze in order to know basically where you are starting from. And after the second one, which is the most important one in terms of objective, is called scenarization module, where it is possible to represent possible future scenario of evolution of the island energy system in order to analyze well the potential benefits of different use cases. That's what it has been done in the scope of this project, but also different kind of efficiency measures in order to reach a given policy target. So here just a few displays of the tool that I will present after with a short demo. So what's main view at the center, you can see it here, is a map view of the island. So here you have a representation of the Bornholm energy system. And you have different views in order to be able to manipulate the model and to analyze the different results. So first you have a parameters table view in order to adapt the input of your model It's also possible to import structured CSV files to be able to adapt the model. You can also use a graphical representation here just to click on the different assets to look at the different parameters. So at the end, the tool, the IPT, handles hourly data. It's also very useful, of course, for the present the variability of renewables, also typical patterns of energy demand. Just for your information, typical simulations are done at the annual level with an hourly simulation. So you have basically a bit more than 8,000 time steps for your simulation. And after you have different KPI that are used to analyze the different outputs of your energy system, and also some hourly KPI if you have to have more insights regarding, for example, here the demand-supply balance of your energy system. Here I'm just focusing on the features. I will explain a bit more after the energy models that are behind the tool right after. And now, so that was the first part of the tool, the island modeling assistance. And after, what you want to do at the point of the tool is to be able to project your energy system and to see what can be its evolution in the future. So for that, the main view is what we call the pathway diagram view, where you can represent different pathway of evolution of your islands. So here it's just two simple baselines with different steps. So from 2020 to 2050, well, here is a baseline and an alternative. And after, in order to be able to represent the evolution of your islands, you have what we call the intervention library. That is a collection of different possible actions you can perform on your island to, well, basically to make its energy system evolve. So after, you can combine these different interventions with, of course, appropriate parameters to represent the evolution of your system. So it can be, for example, development of electric vehicle, penetration of renewable, etc. So different kind of elements. And after, you need to apply these different actions on your energy system, but also to optimize your system, because in the different actions you can perform, it's possible to say that you want, for example, to optimize your renewable generation. Just, for example, saying that you want a given carbon target, and you can say, okay, I can install up to this amount of renewable, and after you will have an optimization of the investment of the, for example, renewable in order to reach your targets and to see after where you will go. And last, of course, different kind of KPI. So here, for example, it's just the evolution of the generation mix of a given island from 2020 to 2050. So that was about the software features. Now, if we talk a bit more about the energy system modeling, so talking about the island energy system, so you have detailed representation of the different energy vectors. So from electricity, heat, gas, oil products, biomass, H2, etc. So we have a very detailed representation of the energy demand with a breakdown by sector, subsector, and end use, which is very useful after when you are using the scenariization module to target very specific actions. For example, if you want to replace part of your petroleum consumption because you are using electric cars, you need to have this specific decomposition here to be able to perform these steps. And after, on the supply side, the user can decide for which energy you want an explicit representation of the supply. So typically it will be for the power side, so electricity system. Heat generation can be useful if you have district heating system in your island, but for other kinds, for example, petroleum projects, that's not really something we are focusing in the supply side, just saying that it will be imported, for example, in the island. So no specific modeling done on this side. And in terms of models, so you have explicit representation of the energy flows within the island, possibly also to represent the import-export from the mainland. And at the end, in terms of modeling, so it's quite similar, probably what I've been presented before. So it's an hourly optimization at the end of the demand-supply balance in order to minimize the total generation costs, taking, of course, into account the different constraints of the different components of your energy system. So, for example, maximum generation for different kind of units, etc. Well, here, just a very brief, I will not spend much time here, just on the energy system and interaction between the different parts of the energy system. So it's very coupled between the different energy vectors. So of course you have the power, the electricity side that can be connected, for example, with the hydrogen layer, with electrolysis, and also with heat networks, with, for example, heat pumps, etc. So just to say that at the end you have a combined representation of the different energy vectors in your simulations, in your models. Now, when we are talking about the evolution of the energy system, which is represented by the scenarization module, like I said before, we have a library of interventions that are used to create contrasted pathways of evolution of the energy system. So typical evolutions would be first on the demand side. So for example, you can have efficiency measures on different sectors, a switch from IC cars to electric vehicles. You can also have a switch from one energy vector, for example, for heating, to another one that can be represented also. It's also possible to represent evolution in the power grid with, for example, new power lines between different zones of your island, but also between the island and the mainland. And of course, investments in new generation plants. And for this part, like I was saying before, the IPT can actually optimize the investments in new capacities over a pathway that are represented by the different steps. So for example, 2020, 2030, etc. to 2050. And typical parameters for this new investment would be, of course, the investment costs, so CapEx, and also fixed operating costs, the lifetime, and especially for renewable, of course, maximum potential that can be installed in the island, taking into account the specific, limitation of the island. And at the end, you have a joint optimization of the operation at an hourly level and the investment over the pathway. So it's kind of like a balance between operation cost and investment over the pathway. And like I was mentioning before, it's also possible to add policy targets like carbon budget or minimal renewable energy target in order to be able to build your pathway without explicitly saying how you want to achieve the target, but just say, I want to reach carbon neutrality. Here are the different investment options I can have. How is it possible? And what would be the optimal generation mix that I need to have to respect this constraint? And well, I think I will not spend so much time on this one, but just to say that in terms of modeling of the scenarization part or on the pathway, so the first part you need to, of course, to represent is the current, the representation of your current energy system. So basically where you are starting from. And after, for the different steps, you will have to specify the different elements of evolution of your island energy system. So if for some of the different elements you already know what will need to be installed. So for example, you have already, you know that you will phase out your diesel generators in 2030. You can say explicitly that their capacity will be 0 in 2030, but for others, you will want to optimize their investments. So basically, we'll just specify a maximum value, possibly a minimal value, and some CapEx, OpEx, just to be able after to optimize. And after the scenarization, optimization is just a joint optimization of everything. I will maybe just now switch to a short demonstration of the IPT. So just give me a second to change my screen. It's going to take a couple of seconds. Yes, should be all right now. Can you just confirm that everything's all right?
Yes, I do see the screen.
Yeah, that's perfect. Thank you. So here in the main view of the tool, what we call the steady view, where you can see all the different energy systems you have represented in your server. So like I was mentioning before, it's a system as a service. So I'm using my web browser to access the tool on a dedicated server. And here I have a collection of, plenty of energy systems model. So we just open the one I want to open for today. So an energy system representing the different islands of the Insulae project. Yes. So here I'm just zooming into the Bornholm energy system. So like I was saying before, the main view is a map view where you can see all the different parts of your energy system. So of course, it's a simplified representation of your, here is a power system of the island. And you can see that you have some nodes that are representing an aggregated vision. So here, I think it's a medium voltage network level of the island. And in cycle around, you have different assets that we call them, representing different components of your energy system. So for example, if I'm using in, so this one are the transmission lines between the different parts of the island. Here, if I'm zooming in, I can open zoom in a bit more. Yeah. Here, this asset is representing solar generation. So the typical parameters would be installed capacity, of course, here of 8.4 megawatts. You have what we call the availability, which is basically the generation profiles that will be used between 0 and 100%, representing where basically the solar generation will be. And that here you have all the data. So if I'm zooming in a bit, you will, of course, find the typical daily pattern of solar generation. And I can open also kind of assets. So for example, for the power demand would be here. Yeah. Well, basically the key parameters would be the demand profile, and similar to what I've shown before, here you have a time series for an annual value and with well, the different values here. I think I didn't mention before, but in the IPT, it's also possible to represent different kind of climatic years if you want to. So I think here you have a couple of them. Yeah, just referred as test cases, but it's just different kind of climatic years. Just need to use colors here to be easier to see. Yes. So here you will see different kind of profiles you will get depending on the climatic years that have been used. I think here it was historical years from 2009 to 2019, I think. And here you have the different profiles you will get for your demand depending on the different weather data. So here, if it's cold or not, basically, for your power generation. And yeah, now I can go to another view. So here is the energy system. So of course, you need to perform a simulation to see how your system will behave. And after, it's possible to go to the indicator view to get the results. And here I can just open first what we call the demand module, where you have this detailed representation of the energy demand. So here, like I was saying before, you have different kind of energy represented here that are on the right: biomass, electricity, fuel, heat, LPG, and oil, and the different sectors represented here too. You have also you have also end uses that are represented. So maybe I can just put them instead of the energy. And you can see that you have also a split between the different end uses. And this disaggregation is especially used in the scenariization module after when you want to have specific actions targeted to a specific end use. So for example, efficiency for heating, etc., etc. And that's basically this level, especially for electricity, after this annual volume. That's the one that is used, of course, at the end when you have your different simulations done to have your supply-demand match at the end. And just maybe jumping to the generation, to the production. So here, so here you have for the generation of electricity for the different nodes of the island. And you will see basically what's produced at each node of the island. You have the same here for the heat, because for Bornholm, we were also representing the distributed heat network. And I think below it's for Madeira Island. And maybe just an example about the temporal views. If you want to have more details on the exact behavior of your island, of course, you can use some detailed temporal views to see how the cumulative generation is done at each hour of the year. So for example, if I'm just zooming in at a couple of weeks, you can see that in 2019, actually, there is already quite a large amount of renewable in Bornholm. But still, you need in gray here some imports from the mainland in order to be able to cover the needs, but not at each hour. So for example, here, actually, there is an excess of generation for the island that here it's not represented, but it's stored in different kind of storage assets. That was for the island harmonic assistance. And now I will go back to the home view to open another kind of study where I have designed a pathway of evolution of the island of Madeira, where I can't remember what's the name. I think I put it here. And that's the one here. Yes. Yeah. So like I was saying before, here I have an example of pathway of evolution. I can just click on the year 2030 to see the different kind of interventions I have created in order to assess the evolution of my island. So here I can see a list of different what we call actions that are representing possible kind of evolution of the island energy system. So for example, here I have a change in demand based on the demography. It's basically just a small percentage of decrease of demand, representing the fact that there is a slight decrease of population in the island of Madeira. You have some efficiency improvement just below, a new optimized onshore wind farm. And for this one, the key parameters would be, of course, the where is the cost? You will have here the maximum capacity. And after, I think I missed it before. Yes, here you have the capex of investment for the onshore wind farm. So that means that if you install 1 megawatt of this wind farm, you will have to pay this amount. And after, the exact result will be an output of the optimization. And typical other kind of action you will have is, for example, electrification of transport. And short, I can just switch to the indicator view and just to show you, for example, what you will get at the end. So I'm going to maybe switch to Madeira pathway. Yeah. So in this example, for example, you will get a decrease of the oil demand. And and an increase of the electricity demand. So here, basically, just mostly driven by the increase in terms of electricity for the transport sector. Okay, I can maybe just switch back for one last slide regarding the commercialization roadmap of the IPT. Just need to change. Yes.
I would, sorry to interrupt you, Paul. I would really suggest you to present the last slide very quickly so that then we can discuss the Q&A.
Yeah, that's just one last slide. It's going to be short.
Sure. Thank you.
And if I can find it, yeah. Yeah, so that's really short. It's just the commercialization roadmap of the IPT. So here, just to say that basically the development of the tool is over. We are still working on it, but now we are starting the commercialization of the tool. So for us, targeted users are any decision makers involved in the decarbonization of new islands, municipalities, utilities, energy authorities, etc. And in terms of package, what we provide is an access to an IPT server with dedicated calculation service for energy system optimization. So you just need for you a way to access the tool, but any computation capabilities will be on the server side. And of course, some support, 100 island example datasets and user community. And just regarding pricing, it's an annual subscription to the IPT license package with a free trial period. So, well, if you are interested in the tool, so, well, you can reach out to me and we can give you more details and create a trial period if you want to. Yeah, that's all for me. Thank you very much.
Thank you very much, Paul. Thank you for the interesting demonstration of the investment planning tool. So it is interesting to see the development of 2 concluded EU projects. We as ETN also coordinated or are coordinating right now a project to decarbonize islands. So it is interesting from our side to see these developments and how far you went. So congratulations for your hard work. So I'd like to open the floor for questions and answers. So we have about 15 minutes. So please feel free to ask any questions to Sergio or Paul. When raising your hand, please identify yourself and go ahead with your question. Thank you. Floor is open. Okay, Duncan, great. Yes, I see you have raised a hand. So please identify yourself and go ahead. Thank you.
Hi there, Duncan Gray here. Just one question for Paul. It's about the IPT tool. Is that exclusively available for Insulae project partners, or would that be, I guess you're looking at commercializing it, so I presume it's just for project partners?
Yeah, that's a good question. So it has been used for the moment only by project partners, but of course the point is really to extend it to other islands. And well, since the project ended a couple of days ago, so now we are really entering this commercialization roadmap. So now it's open to everybody. So it's focusing on, for the moment, EU islands. Even it can have a slightly broader after scope that could be possible. But for the moment, like, yeah, any EU island that would be interested to have an access to it, well, that's who we are aiming at.
Okay. It might be useful to speak about that with yourselves off call, because we're working on a similar Islander project and looking at replication as well. So it looks like quite a useful tool for some of the work packages we're involved in.
Yeah, it's very nice, very interesting.
Okay, I've got your email there from the last slide, so I'll send you something.
Perfect. Yeah, thank you.
Thank you for your question. So the floor is still open. We have a bit of time for any questions you may have. Okay, I will actually ask a question to both of you, Sergio and Paul, because as I just mentioned, Robinson is still in the phase of implementation. So our project started about 3 years ago and still 1.5 years to go. So we are approaching the third period of the project. And as we have some colleagues attending this meeting, we have also been involved in the development of energy management systems. I would like to ask, what are the main challenges that you encountered, technical challenges you encountered so far during the development of your modeling tools? We also like to have this sort of exchange.
Well, I can start. In our case, we usually face two challenges. The first one, as our models are based on data, is to have historical data to model and to work with, and then to put the models in operation. And in our project, well, it was the most tricky part was the implementation of the field devices, communicating with the middleware, and the flow of data goes continuously without interruptions, because they appear some circumstances that the system breaks down, there's no data, there is needed to find why the data was interrupted. And in our case, it was something particular. The project was developed during the COVID pandemic, so we have to face with these issues in order the issue regarding to the installation and the deployment of all the devices that were needed to be in the field, in order to put our tools and the middleware and so on in operation. But basically, in this kind of projects, working with real systems and with real devices, this is a typical, let's say, bottleneck that has to be solved or can do some kind of problems.
Yeah, and that's very interesting. I would say on our side, it's slightly different. Well, data collection is always an issue, so that was the same for us, and collecting the data had been, well, a problem for some islands. And I would say that it's less close to the real operation of the system. So at the end, I would say that we have more historical data that have already been kind of like improved, where you don't have that much like issues in the data. Still, you have some, but that's a bit better. So I would say it's not really our key issue. I would say for us, since the objective was really after to give the tool to the different partners, so especially like, for example, the follower islands and also the lighthouse islands have been using the IPT, not Artelys, just us, and we were just providing some support. So I would say the key part was more like transmission of information, so it was not really technical, but more like giving the right amount of information, because even if the tool is rather simple in terms of its use, it's still quite a lot of work and a lot of modeling tool, and people who are not always involved in energy modeling can have some struggle to harness the difficulty of this kind of exercise. So it was a bit of work to do this, but at the end we're really happy because, well, we had some difficulties, but at the end all islands managed to do their model. Some of them did something simple if they didn't have much of the like technical background, but others did quite advanced models. So we're really happy for this. So yeah, for us I would more say that it's a question of kind of like transmission and knowledge sharing regarding energy model development for people who are not experts in this field.
Thank you both. Thank you, Sergio and Paul. So I do not know if we have comments on these two statements by our participants. Also, considering maybe the experience, maybe it has been a bit different or similar. So I'd like to also open the floor on this topic. Okay, I do not see any questions regarding regarding your interesting presentations. So we're also about to reach the closure of this webinar. So from my side, if there is no further questions, I would like to thank both presenters for the very interesting presentations and also the insightful responses you gave right now in the question and answers. So I hope this is useful also for our sister projects and our partners as well. And after this meeting this week, you also received both presentations, the recording, and you will be invited to the next webinar, which will take place in March. So this is a webinar series of our Decentralized Energy Systems working group. So with this, if there is no further questions from our audience, I'd like again to thank you all and wish you to see the next episode of our webinar series. Thank you very much.